Okay, guys, so let's start. So last time I explained, I just want to tell you in chapter 5, you already know how can you design counters using sequential circuit. But it's gonna be it's gonna be complicated if you do it using sequential circuit. But yeah, this one is the option. You can do that. That's why in this chapter I'm trying to show you a trick or some technique. How can you design counters without going through the difficulty or the design of sequential circuit? So I told you we're gonna design two counters. One is called rhythm, the other one is called synchronous. Uh, there are some similarity between them and there are differences between them. The similarity is usually we use T flip-flops in counters, usually. Yeah? Because you can see, if you can see the figure we have here for counting, yes, if you see any figure of this one, you can see either not change or toggle. And that's T flip-flops. That's why it's very attractive, or usually we use T flip-flops to design counters. One more thing I explained last time, we have two types of counters. One is called rebel, the other one is called synchronous. In case of rebel, as we see here, we have, before I say that, in general, if you want to design in-bit counter, okay, that means you need n flip-flops. So usually the number of flip-flops are equal to the number of bits you have in the counter. Here, in case of rebel counter, you can see we use T flip-flop. It is one. That means it's toggling. Every time there is a clock, you toggle. Clock, toggle. Clock, toggle. We make it this way. However, as you see here, the first flip-flop, the clock is gonna. This one is connected to the clock. Okay. But after that, this flip-flop is gonna trigger the output of this flip-flop is gonna be connected to the clock of the second one. Okay? Same thing here. The output of this clock is gonna trigger next one. Okay? That's why we use the word rebel. Rebel means one flip-flop is gonna or trigger next one. The meaning. The second way I'm gonna explain today, we call it synchronous counter. So it will be different as here, as we see in this case of synchronous, all of them are connected to the clock, the same clock. This is the main difference. Okay? So now, for sure, now I need to do some changes. Okay, so I can't keep this once here. Otherwise, all of them are gonna toggle. Okay? You're not gonna get correct counts. Okay, so that's why you will see today, yes, all of them are gonna be connected to the same block as you see here. But I will control at what time the flip-flop will change and at what time it has to be stopped. Okay? So as you will see, for example, I'm gonna connect the output here to the input here, so that when the input here is 0, so that means this one should be no change. When the input here 1, so this one toggle. Okay, you will see why. But I just want to show you the difference here. These ones here are toggling all the time. Okay, but here every one of them is gonna, for example, as you will see why, I'm gonna explain why. But here the input, the T input is connected to end between this one and this one. Okay, that means when this one is 1 and the output of these two flip-flop 1 and 1, so this one is 1. You will see why I made this. But the main difference between these two is the clock. Clock here is connected, all of them connected to the same clock. Here is a clock of one flip-flop is coming from the previous flip-flop. The first flip-flop is going to be connected to the main clock you have. One more thing interesting we found last time is if I connect, here we have A node and here we have A node prime. This is interesting. So if I select from A node, so actually it's gonna count up. But if I connect here from A node prime, it's gonna count down. So just simple wiring. Gonna count up or down. Okay. I will try to go through it quickly again. So again, everything is started from here, guys. If you have a counter, This is how I start from output to the input. So this is the output I have to get if I have a counter. If I have a count up, that's what I have to see. Yeah, I will say. Now I will think how I can wire the flip-flop to make this one. You see? That's why you can see here, guys. This is the clock. We have here the first flip-flop. You can see the first flip-flop always it has to toggle every time there is a falling edge coming from here. Okay, that's why the way I will do that. So how can you make this one? How can you make this signal? The way I can make this signal is I need to have a T flip-flop that's toggling. T is equal to 1, and then I connect this. The clock is going to be connected to this one, so that every time there is a falling edge, that's as you see it. Falling edge, toggle. Falling edge, toggle. So always, every time there is a falling edge, this one has to toggle. How I can wire the first flip-flop to get this signal? Okay, that's why if you see here, this is the way I did it. Here we have here T is connected to 1, as I told you. The input here is connected to the clock or count, whatever you want to call it. Okay, the clock. So that every time there is a falling edge, toggle. Every time there is a falling edge, this one toggles. Is that okay, guys? This is using T flip-flop. This is the same thing, but using D flip-flop. Because remember, if I connect a Q prime to D, so this one becomes always T flip-flop with input 1, toggling. Okay? So if you have a D flip-flop and you wanna use it in the toggling mode, you can connect it Q prime to D. Okay? Or you can just use T flip-flop. Why? Because you can see every time you have Q prime, it's gonna come to D, and then Q is when clock comes, Q is equal to D. So I'm gonna get here Q prime, and this one will be prime of this value. So always you can find every time there is a clock, it's gonna toggle. Okay. Anyway, this is if you want to use D flip-flop. But anyway, you can just use this T flip-flop. This one. Okay. Now, as I explained last time. Okay. So now I know how can I get this signal. Okay, now for A1, how I can get this signal from A1. Okay, again, you can find if I have a flip-flop, 1 toggling all the time, but the clock is actually coming from here. So it has to toggle at this. So this is how the signal is. Every time there is a falling edge here, this one has to toggle in order to get this signal here. Okay, that's exactly what I did. So what I did here, I connected T here to 1, and then the clock of this one is actually coming from A node. So that every time there is a falling edge here, this one has to toggle. Okay. For sure, you can assume all of them have the same reset connected to a reset. It's a good idea to have reset here so that in the initial value, you have a counter. I want to start from 0. So initially, I can put here 0 to clear all of them. Yes. Again, it's the same thing. How I can get this signal here from E2? You will find it's exactly the same thing. If you have a flip-flop, it is 1, T is 1, okay, toggling all the time, and this signal, this A1 is actually the clock for it. You will get this signal. Same thing. How I can connect this flip-flop to get this signal here, to get me this signal. Again, it's the same thing. Here T is 1, and this one will be the clock of this, as you see here. So always you can see here, all of them are 1s, as you see here. All T's are 1s, and then the clock of the first one is connected to input clock. But here E node is gonna trigger this one. E1 is gonna trigger this flip-flop. E2 is gonna trigger this flip-flop. Now, can you make 1 billion bit counter? You can do it. Yeah, it's just the same way. You can just keep extending. Yeah. Any question? Okay. This is for count up. For count down, okay, you can see here. Uh, this is how the signal it should be, okay, for count down. I here 15, and then after 1 clock it is 14, 13, 12, and so on until 0. After 0, it has to go to 15 again. Repeat. Okay. So let's see what here again. I'm following the same logic. The same logic. Here I wire the flip-flop to have this signal. Okay. Let's start with the first one here. Or from here to here, okay, you can see every time there is a falling edge, this one has to toggle. Okay, so this one, the first flip-flop is actually similar to similar to count up. There is no difference. So the way I'm gonna connect this one here is we have here 1, okay, and then the clock here comes from triggered from input source clock. Okay, so this one here, the first one, is similar to the exactly same thing like count up. Okay, it's not gonna make a difference for count up. Okay, so every falling edge it has to toggle. Okay, however, the difference is this is the difference when A1 has to toggle every time there is a rising edge here, not falling. Every time there is a rising edge, this one has to toggle. Okay, now you have 2 options. One option, this one work with falling edge. So the first flip-flop can be falling edge. Okay, this flip-flop can be rising edge. This one, and it's going to be connected to this to A node, so that every time there is a rising edge in A node, this one toggle. You can do this way. However, this is not the best way to do it. Why? Usually we like to use the same type of flip-flop. Either all the flip-flops are rising or falling. Okay. Sorry, positive edge or negative edge. Okay. That's because you may buy a chip. This chip has 4 flip-flops. Okay. But this is one way to do it. That is why if all of them is the same type, so all of them like falling, what I can do here to have the same impact is instead of connecting A node, I'm gonna connect A node prime here. I'm gonna take A node prime, connect it here. Why? Because if you prime is gonna be, you can use it flip this way. That means every rising here, I wanna A1 to toggle at rising. Okay. Every rising here is gonna be falling in A node prime. When you flip it, it's gonna be falling. Because I'm saying, and because this one is falling, so I wanna. This is the way you can do it. Okay. So again, all what you have to do here, I'm gonna take like a node here to get A node prime. You don't need for sure to add inverter because every flip-flop is giving you Q and you Q prime. Okay. Same thing here for the next one here, from here to here. A node has to toggle when A1 is actually positive edge. However, if I want to use a falling edge or negative edge flip-flop, so again, in order to toggle at this moment, so here I'm going to connect A1 prime. Okay? So that in rising will be falling. Okay? So very interesting. So let me summarize what I said to make it very simple. Okay. So actually, these two, count up or count down, they're almost the same, except the difference is that here, look here. So this one is the same in both cases, up or down. The difference is that if you connect A node here, it's up. A1 up. A2, it's up. But if you connect A node prime here, it's down. A1 prime here, it's down. Very easy, very interesting. A2 prime here, you can count down. Very easy. You see? Any questions? Yeah, that's what I'm seeing you here. So here I'm connecting here Q prime here, Q prime here, Q prime here to count down. Sometimes we like to have like BCD counters. Okay, so just let me define what do you mean by BCD counter. You already know from this course what BCD means. It means we're gonna have number from 0 to 9 in binary, in 4 bits. That's the meaning of BCD. Okay, binary coded number or BCD. I forgot what's the but that's okay. So here it's actually you have 4 bits. You have 4 bits. Okay, these 4 bits can take numbers from 0 to 15, but if you are using a BCD, so actually it should be only until 9. Okay, because this is the decimal numbers we are using. I think binary coded decimal something. Anyway, so the way I can design the BCD counter or counters, yeah, I can do sequential circuit as we did before. It has to work this way. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After 9, it has to go to 0 again. Okay. So you can see this counter is similar to the counter I have here. This counter, however, this counter is going to count from 0 to 15, 0 to 15, 0 to 15. Okay, but I need to cut at 9. After, so this one has to count. This one from 0 to 15. But the other one, it's almost the same thing. Still, you have 4 flip-flops. Okay, but I need to modify it somehow so that it counts from 0 to 9 and 0 to 9, 0 to 9, and so on, instead of content. So after 9, it should not be 10 here. After 9 is 10. But in BCD counter, after 9, it has to be 0. Okay? Again, you can design a circuit to do that. Yeah, you can do that sequential circuit, whatever. You can design a circuit to do that as we explained in the previous chapter. But also here, I want to tell you something interesting, like a trick. Also, we can do a simple trick here. Look at the simple trick. This counter, this counter here is similar to this counter. It can count from 0 to 15, as you see here. So this counter, this is actually 0 to 15 counter. Okay, normal 0 to 15, but I will modify it a little bit so that after 9, I'm going to get 0, not 10. What I'm saying? How you can do that? Okay, the way I can do it here, guys, is when, yeah, so here you count 0, 1, 2, 3, 4, 5, 6, and so on until 9. Okay, so this is 9. After 9, I'm going to make a reset. This is the main idea. So the main idea here, I'm going to add an end here so that once I have here 1 and 1, okay, so once we are going to have here 1 and 1 when it tries to become 10, okay, because 10, 1, 1, 0, 0 is 10. You got what I'm saying? So once after 9, when it tries to become 10, what's going to happen here, because this NAND is going to put 0 here to reset all of them. That's why after 9, I will get 0. Okay? Because once after 9, once it tries to put here 1 and 1, okay, to make it 10, so now because I added this part, okay, I added an end here, so that once I have here 1 and 1, I'm gonna reset it. That means after 9, I will get 0. Okay, so you can see now, guys, what I did is I used again this one way. I'm not saying this is the only way. I just want to show a small trick. Okay, so I used the same counter like this one, but all what I did, I want to cut at number here. Yeah, sorry, this is down. Okay, let me come here. So here, I want to cut here 9. So after 9, it should be 0. Okay, that's why if you see here, this is number 10. At number 10 here, at number 10, you can see once we have here, I think I made mistake. This one should be 101. Is that right? 101. So yeah, so this one has to be 11. Once this one is 11, so I'm gonna reset at this time. Okay. By the way, you can use the same logic so that you can reset at any number. Okay, if you want. So for example, for any reason, if I want to reset after 10, I can connect the circuit so that after 10 you make a reset. Okay. Yeah, so here I got here this the output of this one, which is the most significant bit, and I got this bit as well. That's why I'm sorry, this is not 10. 10 is actually 101. Okay, so this bit and this bit. Okay, this is the most significant bit. So this one is this bit here, and this one actually is this bit here. Okay, once I have one here and one here, okay, so I'm gonna reset immediately. Yes, your question.
You answered it. Okay.
Anyway, I don't want to spend more time. I just want to. You can design it like a sequential circle, whatever how it looks like. But the purpose I'm teaching this one, I just want to tell you, we have different types of counters, count up, count down. Also, we can make PCB counters. Also, I want you to learn this trick, the trick I made it here. Okay. Now I'm gonna move to synchronous counters. Okay. So similar to what I explained, it will be the same thing. But you should understand the way I will think about it here will be different from what I did before. Because in case of ribbon, I know how the flip-flop should trigger the next, that should be a clock for the next one. But this is not the case here. It's not the case. Because in case of synchronous, all the flip-flops are connected to the same clock. But I will see how I connect them. Okay, so the toggling happen at a certain time. So let's see what observation I have here. Okay. First of all, if I look at these two here, from here to here, you can see the first one is toggling all the time, as you see when we have a clock here. Okay, so this one is should toggle because this clock. Keep in mind, this clock is actually connected to all of them. All of them have the same clock. So this one here, node, has to toggle all the time. Okay? So I don't have any problem with this one. So the way I can, in order to get this signal here, okay. So the way I'm gonna connect A node is, yeah, because I'm gonna make something even easier than what I have here. It's the same thing, but I will make it easier. So you may easier for you to remember it this way. Okay. So the first one here, this is A node. Okay. So here we have T flip-flop, and then here I'm gonna connect the clock here. All of them are connected to the same clock, as you know. Okay. So the first one, and this T has to be 1. Make sense? Is the first flip-flop has to toggle all the stuff with the clock. Okay, that's what you see. Now, let's look at E1. E1 here. Look at the observation here. Okay. The observation we have here, E1 has to toggle. Okay. Number one, when every time there is a rising edge, and A naught is 1 at this moment. So if you look at the toggling points here, this one has to toggle here. So at this point, there is a rising edge, and also A naught is 1. Okay, I can see another toggle here. In this toggle, I can see A naught was 1, and there is a clock. Same thing, another toggle here. So again, if you see at what time E1 toggle, you can see the relation between E naught and E1. Every time E naught is 1, E1 has to toggle. That's how it is. Okay? Every time this is a 1 here, okay, this one has to toggle. Every time there is a 1, this one is 1, this one has to toggle. Okay. So how I can connect, how I can wire E1 to do that? How I can wire it? Very simple. All what you have to do, this is E1. We don't talk about clock because all of them are connected to the same clock. We don't talk about clock. So the way I can do it is A naught is going to connect it to the T. So that every time A naught is 1 and there is an edge here, falling edge here, this one took. That's how I can get the signal. Okay? So when A naught is 1, this one here toggle. When A naught is 0, no change. This is how can you see the relation between A naught and E1. Every time when this one is 0 and there is clock, no change. Every time when A1 is 1, there is a clock, toggle. You can see the relation between A1 and E naught and E1. Okay. Now, Let's think about E2. How I can wire E2 to get this signal. How I can do it. Okay, but you need to keep in mind, clock already connected. Okay? Because this is synchronous. So you can see the way I can do it. It's the same thing. You can see, I'm going to see what is the relation between E2 and E node and E1. So you can see here, guys, toggle has to happen when E node and E1, both of them are one and one. Okay? Same thing here. Toggle happen here when this one is 1 and 1. Otherwise, it is, you can see here, in order to get this signal here, A2 is toggle or it has to toggle or toggles, okay, when A node equal to A1 equal to 1. Otherwise, no change. Okay? You can observe it here. Every time A node toggles at this moment here, okay, you can see this one was 1 and 1. Every time 1 and 1, so this one has to toggle. Make sense? How I can select it here? Very simple, very easy. Here, you have here P2. That's okay. We don't talk about clock. All of them are connected to the same clock. And now I need here again, instead of making some, this is my advice to you for exams. I can just say I can make here N and I can say E node and E1. You don't need to make wires this way, and then it will be difficult for me to follow the line. But yeah, I can say E node and E1. Okay? That means T is gonna become 1, and is what then a toggle. This flow is gonna toggle when E node and O1 1 and 1. Otherwise, it changes. If I want it this way, I will get this. Okay? Let's look at the next one. The next one here. And then after that, I need to get a general rule so that if you want to use one
بتكونتك you can do that. I need a general rule.
Okay. So see what happens here. What happens here? This one is gonna toggle when all the 3 previous ones are 1. Now we can figure out a general rule. Okay? So same thing. This one has to toggle here when all the previous ones are 1. So now, in the next flip-flop, this is here T, and then again, all clocks are connected together. Okay. So here I can connect. Here I have, it has to be A node, A1, and also A1 and E2. Make sense? By the way, you can do it in a different way. So it's okay to do this way, or I can make it this way. I can take the output of this one here, and then I can also connect E2. It's the same because this one here is actually E node and E1 and E2. Okay, so now if I want to add one more bit, how I can make it? If I want to add one more bit. So here, I'm going to make AND here. I'm going to take this one here. So this one has to toggle when the previous 3, okay, or all of them are 1s. I'm sorry, all the previous ones are 1, 1, 1, 1. And to do that, you can take, all of them. If you want to add number 4 here. So all of them, all the previous ones are 1s. Okay? And this is the general rule I have here. This one toggles when the previous one is 1. This one has to toggle when the previous 2 are 1. This one has to toggle when the previous 3 are 1. This one has to toggle when the previous 4 are 1s. You get what I'm saying? And so here I can take the output of this one because the output of this one is actually E node and E1, E2, and then I can add here E3 as well. Any questions? In exam, because I told you this part will be, this also can be in the exam. It's okay if you want to draw this signal, it's okay. I use the same signal, but I complicated it a little bit to add like an enable for counter, okay? I will show how I made it, but it's exactly the same thing like this one, okay? Yeah, here, look how I made it here. So this one here is exactly the same signal, the same circuit I did before. But all what I did here, guys, look, I added one input here. We call it enable, count enable. Okay. So that I'm gonna show how it works. So that when the count enable, is it this count enable? So if it is 0, so no counting. I will count it both. You remember when we had X in chapter 5, we had X in order to both counting or resume counting. It's the same thing here. This one. So here, if I put here 0, so it's gonna be no change. Hold count. But when you put 1, it's gonna resume counting. Okay. Let's see how it works. Let's start with, for example, how you connected it. Okay. You can see here, I have here one end. This end has one input here, which is the enable, and one input coming from E node. Okay. This end here, it has E1, okay, enabled with the output of this end. Okay. Same thing. Here I'm gonna add one end. I'm gonna take E2 and the output of this end. Same thing here. If you want to add anything else, always you put one end, okay? You take the output of this here and the output. Okay? So you continue this way. How it works, I will tell you how it works. Let's start with disable case, okay? If I put here 0, okay? This one is 0, so the output of this end is 0. Okay, so regardless what you have, it doesn't matter. If one input is 0, so you are gonna get 0 here. By the way, this is JK flip-flop, okay? You can use T flip-flop, it's the same thing. Because as I told you last time, if you have JK flip-flop, if you connect them together, it's the same thing if you have only one input T flip-flop. I just want to show different cases. But you can, in exam, you can just use T flip-flop. It's okay. So instead of having 2 input, it's gonna be, you can consider this like a T flip-flop. So as you see here, guys, if the count enable, if I put here 0, you can see here we have here 0 0 here to make no change. We have 0 0 here, no change. Then 0 0 no change, 0 0 no change. All of them, all the T values here. So again, because I tie JK together, now it became T. So all T values here are actually 0, no change. Okay. However, if I make it 1, now it should count normally. How it counts normally, as you see here, when I put here 1, E node is gonna go to the T here. T. So here T equal to E node. Okay. T here, T is this one here. I'm gonna take the output of this one, which is E node and E1. If you see this one here, I'm gonna take the output of this one, which is E node and E1 and E2. Okay. So if you see these values here, it's exactly similar to what I explained here. The first one has to be E node. The second one has to be E node and E1. Third one has to be E node and E1 and E2. It's the same thing. In the exam, if you want to do this one, I'm totally fine. If you want to do the simple one I explained here, I'm also fine. As long as you show me, number 1, the clock is connected to all of them because it's synchronous. Number 2, T of the first bit here is always 1. And T here is the output of the previous one. And T here is end of the previous 2. T here is end of all the previous ones here. So now you know how it works. You got it? Any questions? Now I will come to synchronous countdown. So this is count up. Now I will do the same thing. I will show you if this one is counting down, this is how the signal should be. 15 and then 14, 13, 12 until 0. After 0, it has to go to 15. I will do the same thing. Number 1, clock. Number 2, I need to find how I connect E node, okay, so that I get this signal. How I connect E1 so that I get this signal, and so okay? You will find something interesting now. Okay? So number 1, for E node, it's always toggling when there is a rising edge here. That means the way I have to connect it is here you have three flip-flops. It's always one, okay, and then it's a clock. So that every time, again, here don't be confused, because sometimes I design the counter when it at falling edge, sometimes at rising edges. There is no difference, right? So you can design either way. That's why here in the slide, I'm not just using one way all the time. Okay, you can design this way or that way. So here I'm assuming here we are positive edge. Okay, so you can see here if the clock is, or if the flip-flops are positive edge, so that means every time there is a rising edge, as you see here, it should toggle. So how can you get signal like this one? Yeah, now let's look at the second one here, A1. Okay. My observation here is A1 has to toggle when the previous one is 0, not 1. This will count down. So every time this one is 0 and we have a clock, this one toggles. Every time we have a 0 here, you have 0 here, and clock toggle. So this one always has to toggle when actually the previous flip-flop is 0. Look, it's very interesting. Look here. So the way I will connect it is, you have here a clock. All of them have the same clock, as I said. T here has to be A naught prime. How this is different from count up? Count up, it was A naught. You see? So again, if you connect it to A naught here, this count up. If you connect it to A naught prime, it's going to be count down. Make sense? Also, if you look at the observation I have here as well for A2, so here actually, when the previous two are zeros, this one has to toggle. Every time this 0 and 0, it has to toggle. 0 and 0, it has to toggle. Otherwise, to change. How I can design it again here. So this one has to be A naught prime, A1 and A1 prime. It's the same thing as count up, but in count up there is no prime. Makes sense? Same thing here for this one as well. This one, A3 has to toggle when all the previous flip-flops are zeros, not ones in count up. Zeros. You got what I'm saying? Okay, guys, any questions? Let me tell you something also interesting here. Look here, guys. That means, number one, if I wanna, in case of synchronous, if you have here multiple flip-flops, number one, all clocks have to be connected together. That we don't talk about clock. We agree on this, right? Because all clocks have to be connected together. But now the trick is, if I connect E naught, it's gonna be up. But if I connect E naught prime, it's gonna be down. Same thing here. I have here end. In this end, if I connect E naught and E naught, so if I select E naught and E naught, it's going to be up. If I select E naught prime and E1 prime, it's going to be down. Makes sense? That's why I can design a circuit. Okay? This circuit has some input selection here. In this selection, I can ask to count up or count down. So that if you wanna count up, the circuit has to connect E naught here. Has to connect E naught here. Make sense? But if you select count down, it's gonna select E naught prime. You can do logic select. Okay, that's why you can buy a chip. The same counter can be up or down based on your selection. How can you do it? Very simple. Based on your connection, either I connect E naught and E1, E2, or selection, or I'm going to select E naught prime, E1 prime. Okay? So the same chip, you may buy a chip. This chip can be count up or count down. This is the application. Some application, for example, I want to count up and then count down, count up, count down. Some application or some chip only count up or only count down. Okay. Some of them it can do both, count up and count down. It's the same chip. based on your selection. And that's what I'm going to show you now, but it's not going to be in the final exam. But I just here, so you can see here, it looks a complicated circuit, but it is not. You will see now how it works. So here I have selection here, okay? We have two input, one up and down. So here, if you want to count up, you can put here 1 and X. So what X means, whatever you put here, it doesn't matter, okay? You will see what I mean now. Now, if you want to count down, you have to put here 0 and 1. If you want to not change, you put 0, 0. Like you pause here, no change. Okay? So now it's just one circuit. This circuit can count up, can count down. You can pause, or you can resume counting. You can do all of this based on what value you have here. Okay. How it is connected? As I told you, if the selection is counted up, the circuit you have here has to connect. I have to take E node. So, okay, that's why you look here, guys. We have two branches. One branch for E node, one branch for E1. Sorry, for E node prime. So one branch for A, one branch for prime. So that if you want to count up, I'm gonna take this branch. If you want to count down, I will take the other branch. That's what you see here. Look here, guys. Here I connect E node here, and then the output of this one I connect E1, and then I connect E2. So it's very clear. If you wanna count up, you have to activate. You have to activate this branch. If you want to count down, if you look at the second one here, the second branch you have here, this one, it takes E node prime. So that means if you want to count it down, you need to activate this one. How can you do that? From the input, from the values of the input. So from the values of the input, either activate this one or activate this one. If I activate this one, so by this way, I'm going to connect E node, E1, and it was E node, so I'm going to use ACE. But if you activate the second one, I'm gonna connect the prime. And once you connect the prime, because it's very interesting. Just if you wire A, it's up. If you wire prime, it's down. And actually, if you don't activate both of them, this will be no change. So now I should have 3 cases. Either you activate this one, or you don't activate both. How this works? Like you see here, guys, number one, if here I put 1 and X, whatever you put here, it doesn't matter. Okay, why? You will see right now. If you have here 1, so here this inverter will make it 0 here, and then you have 0 here. Once this one is 0, you actually cancel this bridge. Because 0 and because this and, if this one is one input is 0 for and, output is 0. Output is 0. Output is 0. You already canceled this branch. Okay? And now, because this one is 1, this is how you told us you can activate or deactivate. How can you do that? Very simple. If I make here 0, so everything here is cancelled because it's end. But okay, if I want to cancel this one, I'm gonna put here 0. Cancel this branch. Put 1. If you put 1, you activate. 0, you cancel. If I put 0, 0, 0, 0, so actually both of them are gonna give you 0. 0. No change. So let's look at this case here. So here, if I put here 1 and nothing here, actually what happens here, I will get here 1, and then I'm gonna connect E node here. I'm gonna connect here E node and E1. We're gonna connect E node and E1, E2. This connection is for up. That's why it's cancelled. Okay. Now, if I put here 1 and 0, okay, 1 and 0. Once you have 0 here, so this part is 0, this one is 0, so you cancel this bridge. And here we have 1, you activate this bridge. You have here 1. So here I'm gonna get E node prime, E node and the E1. Everyone is prime this way. So this is counted down, right? The last thing we have here, if you just put 0, 0. If you put 0, 0, this branch will get 0, this branch will get 0. So here, everything here is 0, 0. So actually the input of the flip-flops, all of them are gonna be 0. And you know, in case of T flip-flop, when the input is 0, it means no change. Your question?
My initial question was if you could take out the down input and the first AND gate and just do up and up primes, but then I realized what you just said, that if you want to pause.
Yeah.
Pause on it.
Yeah. So actually, every circuit I put it here, it's like a multiplexer somehow. So for example, here is if I put here 0 and 1, so you are gonna allow AR to come here. Okay? This is selection. But if I put here 0 and 1 here, so you are gonna allow AR. So either A or A prime, based on your selection will be here. Okay. So here again, if you see how I designed it for each input, you can see, guys, if I put 0, 0, so actually you then I will get 0. Before I talk about the last one, maybe I want to take 10 minutes to talk about the final exam. Because nothing else I will explain.
So as I
in my email, guys, the first question will be simplification using algebra manipulation. Maybe this is the second or third time. Third time I test you in algebra manipulation. It will be similar, something similar to the question you have in test 1, right? And also in quizzes. So I will give you a summary. I will give you the notes, what I did in test 1. Okay. Simplification using key maps. I'm repeating these two because this is very important in this course. Simplification using key maps. So again, similar to test 2, I don't think I will bring three variables. 3 variables is too easy. It's going to be 4 variables. Okay, it's going to be similar to test 2, but this 2 was product of sum. That's why you have. If you want me to repeat, you need to summarize zeros, not ones. You need, if you need me to give you example, I can give you example about this one. So if you already have too many examples actually in this chapter, okay? So you need to learn, if you have 4 variables, okay, how can you simplify using sum of product or product of sum. So okay, similar to test 2, but test 2 was about product of sum. Final may be product of sum or sum of product. You need to learn both. Is that okay, guys? And they actually it's the same. The only difference is they are very close. You have a map. For example, okay. If you have also it may have don't care. You know what don't care is, okay? So it should be easy. So for example, if I have something like 0, 0, just some random number, 1, 1, 1, 0, 0, 1, 0, 0, 1, don't X or don't care X, 0, 0. If you have something like that. Okay? So as I explained before, number 1, if it is sum of product, if it is sum of product, you have to group the ones, not zeros. Okay? And it's not a must to group all don't care. Okay? You don't need to group
make bigger groups.
So in this case, I can make, you need to show me the groups, guys, because you can't just, how you read it if you just give me
a magic formula at the end, okay?
How you make groups, okay? So for example, I can take this 2, 4, and then I can take this one. This, in this case, this don't care is going to help me. And then after that, the formula you will get F equal whatever. And that's it. However, in test number 2, I asked you to give me in product of sum. And you have, I think, a couple of examples. It's almost the same thing. The only difference is that in case of product of sum, you have to group the zeros, not the ones. And because you are grouping the zeros, what you are going to get is not F. If you group the ones, you will get F. If you group the zeros, you are going to get F prime. And I want to get F prime. Because this F prime is going to be in some any number. So like, for example, F prime equal XY or WZ, whatever. So now if I group zeros, for example, here in this example here, Yeah, I can take these zeros together. Okay. And then I can take these 4 zeros together. Okay. Then I can take these 4 zeros here, this one solution to do it. So now I will get whatever you have here, but it's going to be F prime. F prime is sum of product. And then after that, if you take De Morgan here, in order to get F, if you take De Morgan of this one, so F is equal to XY or WZ prime. After the De Morgan.
And now it becomes
Any question? You have to do the example twice, like yeah, what goes?
Would it become X plus Y times?
Man, this is just a random thing. I'm not solving it. Okay. So yeah, you need whatever you have here, you have to put it here. It will be in the format of sum of product, but this is F prime. That's what I'm saying. I just wanna make a very quick restriction. Okay. So number one, this question will be a four variable. It may have don't care. You need to be familiar with how can you do it using sum of product or product of sum. Very important when you do it, you need to show me the groups, guys. Please have some mercy on me. You just how
you shouldn't give me a magic formula at the end. How I can know you understand it or not? You can understand?
So you need to. Anyway, so for chapter 4, these are the things you need to study for chapter 4. Number 1, I can ask you to draw any bit comparator. In here can be like 3 bit. I think in the slides I explained 4 bit, I guess, but you should be familiar. How can you do the same thing using 3 bit or 3 bit for me? Especially for comparator, if you remember, if you go to the recorded video, you have the circuit, you have somehow complicated in the slides, but I made it much easier when I explained in the lecture. You can, whatever you want to do, but it will be easy for you and easy for me if you just show how I made it in the lecture. Okay. So for example, in case of equal, you need to go back to see, it will be easier for you even to memorize. Okay. For example, equal, you can have here x1, x2, x3, x4. This way, and then that's it. This is equal. But you need to tell me xi in general, whatever is xi is equal ai. I think it's exclusive no this bi. That's it. This would be much easier than what you have in the slides. Okay. Same thing for the other ones. Okay. Again, if you wanna take the one in the slides, that's totally fine. But this one easier to understand because 2 numbers are equal when E1 equal to V1, okay? And if they are equal, X will be 1. E2 equal to E2, again, it will be easier for you to memorize. Right? Also, you need similar to test 2. I can also ask you to give me any bit other or subtractor, similar to test 2. I can also ask you write the truth table and to do the logic circuits for encoders, decoder, multiplexer. I will not be picky here. I will not be picky. I'm going to say just encoder, decoder, multiplexer. In the slides, we have different types of encoders. One is a normal encoder and the priority encoder. I think the normal encoder will be easy. Just you can do it. You get what I'm saying? You don't need to make it difficult for yourself. I will not say this one. So just as I tell you, show me the truth table and show me the logic circuit of the. For sure, I will tell you what this encoder is. For example, 8 to 1 or sorry, 8 to 3 or something. I will be very specific. You get what I'm saying? But also same thing I think for decoder, multiplexer. Also, as far as I remember, we had different types. Some of them have some of them active low, active high. Just make it. I will not be specific. Okay. If you can take the easy case, regular one. Yes. You have question?
Well, I was gonna ask internals or just the block.
No, man, this is a very important question. I see logic circuit because some students and for sure you can't get some students give me a block. Okay, so this encoder has 8 inputs and then it has 3 outputs. When I say logic circuit, so you need to show what's inside here. What is the logic circuit here? Okay. You can still draw the block, but that's not what I'm asking for. I'm asking about the logic circuit. Same thing. You need also you have some circuit for how can you multiplier x bit by y bit multiply. Okay. Sure, I will be very specific. I will tell you I want to multiply 2 bit by 2 bit. I want to multiply 3 bit by 3 bit, whatever. Okay. So all of them are the same. If you understand one, all of them should be the same. Okay. I'm not sure. I don't remember if this part. There was a more simplified circuit than you have in the slide. I don't think so. But anyway, as long as it's correct, I'm okay. For chapter 5, you need to know how can you design a sequence detector for a given sequence. Okay. That's all what I need from this chapter. It will be, you already have several examples. You already did the project, one part of the project. I will give you a sequence and I will ask you to design sequence detectors. Okay. So if you know how to make one, so
all of them will be the same.
okay? I will explain several things here. But I'm very specific here. Okay? I will ask you to draw the state diagram. Okay. And then you know from the state diagram you have to make the state table. Okay? And then from the state table you have to write the equations. If anything is missing here, you can't continue. Number one, you have to do the state diagram. Number two, from the state diagram you have to make the state table. From the state table you can make equations. Okay? That's it. That's what I will do. So I almost give you the question, but I didn't give you the sequence.
Okay.
Very specific here. Again, you have all lectures recorded, just in case if you want to go back and see how I explain it. You already. So in test 1 we did generator. Sorry, test 2 we did generator. Here we did detector. Okay? Finally, the last chapter also here. You need to how to draw in bit. In here, I will be very specific: 3 bit, 4 bit, 5 bit, whatever the number I will give you. A parallel loop register using D flip-flop. Also, you need to know how can you draw in bit shift right or shift left or rotate register. Okay, using D flip-flop. Okay. Also, I explain how can you do n bit rebel counter using D flip-flop. Okay. How can you do? I'm not gonna ask you to give me the timing diagram. I don't want to. I don't want to memorize anything. If you already understand what I said in the lecture, how we connect them, right? Same thing for synchronous count. Any question here? Okay. So the last part here in this course, it's not going to be in the final exam, but this is, I want you to learn it because again, you remember in the, if you remember in the first lecture, I told you the purpose of this course is not to design a digital system. I might have as an example. The purpose of this course will show you how can you do some operations, how can you do some circuits using hardware. And then this circuit, you are gonna in your future courses, you should know how can you use what I think in this course to use a computer system, a digital system. You know what is decoder, what is multiplexer, what is counter, how you digitize counter, how can you develop arithmetic can do some arithmetic operation like multiplier, other, and all these circuits. They will put all of them in registers, okay, shift registers, all of these are components that are used in any business. One of the things that also used in digital system, what we call memory, okay? So for sure, your smartphone is an example for digital circuit has memory. Same thing for any computer system will have memory. So here, when I say memory, I mean random access memory. I don't mean the external memory. No, I mean the random access memory. Okay, this is the memory. Once you finish the power off, everything is done. Okay, so if you will learn in the future, memory are really this kind of memory. I'm not talking about the memory used to store your pictures, videos, permanent memory. Okay, I'm not talking about this one. Okay, I'm talking about random access because this random access memory should help
microprocessor to execute instruction. This is the part of the system.
But anyway, so actually, as you should learn in the future, why we need a random access memory here? Because actually, your program, once you write your program in assembly, your program is going to be converted to machine code. It should become like a bunch of ones and zeros this way. Okay, so your program is stored in the RAM. Also, your data also stored in the RAM as well. Okay, and yet actually, what should happen when microprocessor want to execute in instruction, it has to read the machine code of this instruction first, and then the hardware is going to execute with. So you will learn in 3130, you will learn for every assembly instruction, you have a code. Okay, machine code. This machine code, okay, the people who designed the microcontroller give us this code. So using this code, if you put it, the hardware is designed. If you have, for example, this code is multiplication. The hardware is designed. When you have this instruction, the hardware is designed to do multiplication. What I'm saying? So everyone is how they design. So actually, what happens? We need to read the instruction, okay, from memory. Also, if you have some data to store, you store it in memory. Sometimes you also need to read some data from memory. So you actually, that's why here is the first picture here. I want to show the relation between microprocessor and the memory. Okay, so all the time, so something is done all the time. All the time, microprocessor needs to read from the memory, write to the memory. Read from the memory, write to the memory. I want to show the relation between both of them. So for memory, I can show like a diagram for memory. You can imagine memory. It's like locations. You have locations in the memory. Okay. In every location, I store 1 byte. You can in every location you can store less than a byte or more than a byte, but this is something that is standard. I think all companies are doing it. In every location, you store 1 byte of information. Okay? So now you can think and memory about it. In location, it's like you have location. In every location, we store 1 byte. For example, here as you see, in location number 0, I'm storing this number, FF, in binary for sure, binary, but I'm writing here in hexadecimal. This is easier for me. In location number 1, I'm storing a byte. In location number 2, I'm storing a byte. In location number 3, I'm storing a byte. So you can imagine a memory like location. In every location, you store 1 byte. Okay? This location, we call it address. That's why if you want to read from the memory, I can't tell the memory, read memory. Memory. True. So when you read from the memory, you have to tell the memory, I want to read location number 20. You need to give the address to the memory. Okay, that's why you can see here. This is how it is connected. Okay. Number 1, you have addresses. You have here a microprocessor has to give the address to the memory. If I want to read location number 20, I have to write in number 20. I have to tell the memory which location do you want to read. Also, we have some control signal here. One is called read or write. You need to tell me as a memory. You need to tell me what you want to read. You want to read or write. Yeah? That's why either 1, 0. That means you want to read. This is how you can the memory and microprocessor. If you give me here 1 here and 0 here, you are telling me I want to write. Okay. Also, we need some. This is the data here, which usually 8 bits. How they are connected. Here I'll give you some example. How can you read, or how reading is done, how writing is done. Okay. If you want to read, for example, here guys, I want to read location number 70. I want to read the byte. The data, which is a byte, is stored in location number 70. How I can read it? Number 1, the microprocessor has to put it 70. Number 2, has to tell the memory, please, memory, stop the reading. How this can be done? You have to put here 1 and 0. Once you put here number 70, once you put 1 and 0, the memory will understand you wanna read location number 70. The memory will go to location number 70. Whatever there, for example, 3A, whatever the number there, is gonna output it here. On this 8 bits, and then you can read it. This is how location is done. This is how read is done. Reading is done. So again, In order to read, number one, you need to give the address. After that, you need to give the instruction to the memory. The memory is gonna internally, this is how it works. Internally, the memory, whatever you have here, the memory will get the byte stored in this position and then put it here, and then you can read. Okay. What about if you wanna write? How it works if you wanna write? Okay. If I wanna write, for example, in location number 80, I want to store number 3A. I want to store number 3 in location number 8. For example, how can you do that? Number one, here in address, the microprocessor has to put 80 here. Number two, in the data, I have to put 3A. It says the memory, because the memory starts working when you give the instruction, you give the command to the memory. So after that, you give the command to the memory to say write. How I can say write? I put here 1 and 0. Once here you put 1 and 0, the hardware circuit here, the hardware of the memory here is gonna go to location number 80, and then it's gonna take whatever you have here, which is 3A, is gonna put it here. What about the old value? It's gone. Overwrite whatever is there. Okay? You overwrite. So again, once I do a writing operation in one location, you overwrite whatever is there. Anyway, so this is how it works. Okay. There is a relation. So I told you guys, usually this data usually 8 bits because it's something is standard. You can design it to make it whatever you want. You want to store in every location 16 bits, 20 bits, it's up to you, but it's standard. All now in every location we store only one byte. But anyway, so this is always 8 byte. However, there is a relation between how big is the address and how many bits we have here in the address and how many locations we have. How big is the memory? Okay? The relation is if the address is n bits, that means I can have locations up to 2 to the power of n. Make sense? Why? Because in n bits, you have n bits, that's what I taught in this course. In n bits, you can have numbers in total 2 to the power of n numbers. Okay? So that's why if the address is n bits, that means I can create how many addresses I can have 2 to the power of n. Okay? That means for example, if you have 3 bits, assume the address is 3 bits. So your memory, it cannot be more than 8 locations in the memory. Because 3 bits can have addresses from 0 until 7. 8 addresses. It can be less than 8 locations. Here I want to give you the relation between the size of the address and how many locations you have in the memory. That's why the bigger the memory, you should increase the size. Here I want to give you number one, you already understand here, from what I explained here, you understand how it works. If you want to read, you need to get some numbers here, and then you have to put 1 and 0, and then the hardware here will give you the value, put it out here. Okay? So I want to give you like a very high level explanation how the hardware can do this. How the hardware, once you put an address and you put 1 here, the hardware will get whatever value is it and give you at the output here. How something like that hardware can do very high level description. So for example here, I'm explaining, for example, if you have a memory like this one, you have address here. This is the address. This is like a very small memory. I'm assuming in this memory we have 2-bit addresses, only 2 bits. Okay, and then that means we have four locations. So this is 1 location, 1 location, 1 location, 1 location. Okay, in every location we store only 2 bits. So here, this is again, I'm assuming this is a choice just to get some idea how hard you put address, and then you get you put 1 read. So how the hardware will read this situation, and this is the other. Okay? So for example, here this is one So the way, for example, here, and then as you see here, we have 2 write enabled, output enabled. So this is for if you want to write, so here you have to put 1 here, you have to put 0 here. If you want to read, you have to put here 1 and 0. Okay. So I will show a very high level description how it works here. I'm assuming every bit is stored in something like flip-flop. In reality, it may not be a flip-flop, but it's a storage unit or a storage cell for one bit. So yeah, so for example here, guys, as you see how it works, I have here a decoder. Okay, when the address 00, so this decoder is gonna output here 1 and 0 everywhere. When you output here 1, that means I'm gonna work on this unit, but this is address number 0. So here, this information is address number 0. This one here should be address number 1, address number 2, address number 3. So that's why I have a decoder here. This one, the address you have here, either I'm going to select this one or this one or this one or this one. So in this specific example, I put here 0, 0. That's why I have here 1. That's why I'm going to work on this one. But let's continue. Here, I wanna read. That's why here I put here out. We enable a good here. If we do that, the link is here, as you see here. So here we're assuming this unit, it has an enable input. Once you enable, so the stored value will be connected here. That's why you are gonna read. So again, guys, as you see here, because I select here, I put address 0. This one is 1, and because I wanna read the out, this end here is 1. You can imagine if I want to read location number 1, so actually everything I'm explaining here is true, but it will be here on this row. So as you see here, once I enable this unit is designed so that once I enable it, the stored value will be connected to the out, and then you can read it if you want. Okay? That's how can you read any location. Now, how can you write? Okay, so if you want to write, here I select 0, 0, but for here, write has to be 1, read should be 0. If you do that, so this end, again, guys, this is just
a very high level sketch. I just want to give some idea about how we
are going to enable read or write. So here, if you put here 1 and 0, you can see here this one here, because this is 0. So here enable will be 0 and 0. So enable here means whatever is stored you have to output. This is the meaning. But now the one will be connected to the clock. Here. So that means I will trigger a clock. So here when you put 1 in the enable, you are gonna make actually a rising edge here. Once you make a rising edge, what happens here for these two flip-flops, in the very beginning, I selected these two flip-flops. I'm working with these two flip-flops because of this address. If you change this address, you may work on these two or these two or these two. Okay? So now, once you select here, once you put here 1 and 0, you are actually, and this one originally was 0, now it becomes 1. So you are going to make a rising edge in the clock. And you know, for example, if you have something like D flip-flop, once you have a rising edge, so whatever you have here in the input, it's going to be stored. You are going to write it. That's how you write. The also value is that. Any questions? The last thing maybe I want to teach here is the last part here, guys. The last thing I want to teach. Sometimes you can notice in our your memory, you have to check, right? So maybe if you have 3 racks, you can put only 2 or 3 and so on. Okay. So that's what I want to show here, how I can use a decoder so that if I have 1 key for 1 key system memory, this memory is 1 KB, 1 KB, 1 KB, 1 KB. How I can connect them together to create a memory that's 4 KB. What I'm saying? So here, just I'm gonna use a decoder so that if you have 4 different key bytes, so now I can connect. By the way, we have something like that in decoders, if you remember, in decoders. If you have, I think 2 to 1, and then 2 to and then you together. So here, what I'm gonna do, guys, is that I have 4 chips, 1, 2, 3, 4. Every chip is 1 KB. I want to connect them together so that it creates okay. This memory is actually 4 KB. Okay. So you can see how it works. It's very simple. Look how it works, guys. Okay, this memory is 1 KB, and I told you there is a relation between how many location you have here and how big is the input address. The location, if this one is n, this one should be 2 to the power of n. Because this is 1 KB, so the input address should be 10. A0 to A9, A0 to A9, A0 to A9, A0 to A9. Is that okay? Now, my address, because I have 4 kilobytes, that means how many that my address should go from A11 all the way until A11, A10, and then A9 all the way until A0. This is the address. Okay? So what I will do, I'm going to use the first 10, A0 to A9, connected to all of them, as you see here. A0 to A9, A0 to A0 to A0 to what you say? But I'm going to use the last 2 bits to select 1 out of 4. What I say? So the first 10 is connected to
all of them.
all of them are going to work at the same time. Okay? So he's going to decide, that's why the first 2 bits here, or the last 2 bits, I'm going to connect them to the decoder. That's why you see here, if I put 0, 0, that means this one will work. But if I put here 1, 0, so this one will work. If I put here 0, 1, this one is working. Okay, and so 1, 1, I'm going to select this one. That's why the last thing I want to teach here, if I ask you, so what is the range of addresses here? 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 Okay, very simple. Look here. All the addresses here, A10 and A11 are 0, 0. So here it should be 0, 0 for the whole addresses here. Okay? And then after that, the beginning address, you should have 9 zeros until 9 ones. Okay? Because this part is common between all of this. Same thing for the second one here. Okay? So it has to be 0, 1. These 2 bits are common for all of them. And then, what is the first address and what is the last address? Actually, it should be from 9 zeros until 9 ones. And if you see here, you will feel we are consecutive. So you will see right now. So here, the first one starts from 0, 0 until 3FF. Next one, what is after 3FF? Should be 400. Next one from 400 until 7FF. Next one should be what is after 7FF? 800. Yeah, it's all from 800 until BFF. What is after BFF? Should be CFF until FF. I think that's enough. Okay, guys. I hope you enjoyed this course. I think that the deadline to do the evaluation is 28. So this is very important. You need to do. Okay, thanks, guys.
Thank you.